And what's unique about the approach that Codetta has developed is the technology combines both digital PCR and real-time PCR on a single sample at the same time. So at high concentrations of target, most of the beads will have one or more target molecules bound to the beads. And we show that in the cartoons on this slide to the right of the digital to analog transition, where you see most of the, or all of the wells generate a PCR signal. And because the technology monitors fluorescence as a function of PCR cycle, you can measure a PCR amplification curve for each bead in the array. So by averaging the amplification curves for each type of bead in the array for all the positive beads, the system can calculate a CT value and then use that to measure the number of target molecules per sample. At lower target concentrations, where majority of the beads have less than one target present, the algorithm automatically switches to then measure and calculate the target concentration by digital PCR. In this case, the system counts the total number of beads for each target of interest, and then the percentage or positive fraction of those beads that generate a PCR signal. And by measuring that positive fraction and applying some statistical analysis, the system can calculate the number of target molecules or target per reaction. So by combining digital and qPCR in a single measurement, we can develop assays that span a very broad quantitative range. So that's depicted in the graph at the bottom of the slide for an IL-6 immunoassay showing quantitative measurements spanning 6 logs, where the 3 points of the curve to the right measured with qPCR by calculating the average CT value, and the 3 points to the left of the line are measured with digital counting. And you can see that results in a very nice quantitative measurement for IL-6 spanning, again, 6 logs of measurement at a single dilution.